Hello everyone, this is lecture 7 of PTRE 46531 Petroleum Reservoir Geomechanics. Today we will carry on with Module 1. We are approaching the stage where I will be giving the first homework, but we are not quite there yet. I think we are gonna be there either after this class or after Monday's class. If we are there after this class, I will upload it tonight and it's gonna be due the next Monday, 23rd, I believe. If we are not there yet, I will upload it after class next Monday, and I believe should be due like Wednesday. I kind of prefer the second option because that gives you 2 office hours for help, but I have to make it clear that I'm not going to be giving answers if you come to the office hours. It's not like don't come to the office hours asking me to do the homework for you. I mean, this is not how it's how learning is. You have to make yourself think about the project, about what you are asked to do, and apply what we learn in class, etc., etc. Now, also it doesn't help a lot that there is not a lot of audience. So it's like, I don't know if you have any questions. I don't know if you understand what we cover in class unless you give me feedback. So that's one challenge with online courses and little on-campus attendance. Okay, last time we proceeded with we wrapped up what we learned about eigenvalues, eigenvectors, and then rotation of coordinates, which was basically I was giving you an SP, the principal matrix, principal stresses matrix, which is basically the eigenvalues, and you had to rotate the matrix to a specific frame of reference. The one that we are using is the most common in the geomechanics, is the north-east down right-hand rule. You have east with your index, north with your thumb, down with the middle finger, right? And then basically, this is how you have 3 angles, alpha, beta, and gamma. And we try to combine the Andersonian stress regimes with the Euler matrix to simplify it to a matrix that has only 0, -1s, and 1s. And I think we did a good job in example problem 2 all the way to 4 to 5. It was pretty good. Well, example problem, yeah, all the way to example problem number 5. And then we started talking about how do we estimate those stresses, because now you know what is SV, okay, but you don't know how to estimate it. And we started talking about how you do that. There is a subdiscipline of structural geology dedicated to that task. And these people, of course, they use different measurements, etc. It's not a very lucrative subdiscipline, but they basically solve this equation. They get data on the density, maybe a density log or other stuff, and they solve this integral. Okay, every layer has a density, and then you multiply that density with the height of the layer, and you create a pressure gradient, actually, sort of value, and you basically add it up to a big pressure value. That would be the SV at the point of interest, which in this case, the schematic on the right is basically right directly below ZN or at the ZN point. Like I am, let me write it. I am looking for SV here. question mark. What is SV? There. And basically I have to solve this SV. I have to solve this equation, this integral. Now, it's rare that nature is gonna give me an equation of how raw bulk is varying with Z, right? It's not like I'm gonna get an equation of how raw bulk as a function of Z. It's unlikely unless it's an idealistic situation, like a homework question or something. It's unlikely that you are gonna be given or like you have data that you are able to feed a function, basically an equation. It's unlikely that you are gonna have that. So most likely you are gonna have to resort to an approximation, which is what we have on the right with the sigma. It's a summation of raw bulk multiplied by G, and then the delta Z, basically the height of that layer. And we talked about how if you use American units, if you use pound mass, you do not need to multiply by G to get the pound into pound force. But if you use SI units, you sure have to multiply by G to get the pound, to get the MPa or the Pascal, basically.
The 9.81.
Yeah, the 9.81. And we said a good rule of thumb, an easy number also to remember, if you don't have any data, and it makes sense for things that petroleum engineers are worried about, if you don't have any other indication, you can assume that the lithostatic stress is 1 psi per foot, which translates to 23 MPa per kilometer. It's a good approximation, rule of thumb to have in mind. Now, what about offshore? If you are offshore, you have this. There, different layers of sediment, different zones, but then on top of it, you have seawater. The seawater weighs, it has a weight, and this weight needs to be accounted for. So we need to take the turquoise color weight and add it to everything that we get for the Earth to get the SV. So it needs to be incorporated. The weight of the seawater needs to be incorporated. There are many ways you can be given the weight of the seawater. In the homework, you are going to see a very, very weird way that can be given to us. But here, an easy way is like by giving you the pressure gradient, like for Gulf of Mexico, 0.465 psi per foot. I think it's a logical number for the salinity of the water in the Gulf of Mexico. And you can you may have this is not an equation, this is another approximation like the previous one. It's if you have the density of a layer and then you have the depth at the middle of the layer. So it's basically the trapezoidal rule, but it's shifted on the side. Okay, so it's not necessarily for offshore, but remember, for offshore, you need to add the weight of the water above everything, but you don't need to be adding it at every layer. That's a common mistake that students do when they are doing offshore exercise. They find the weight of the seawater and they add it to every layer. And then you create a recurrent mistake. You find a very big value for SV, which is not the case. This equation, I put it here because of what you will see, I think, in homework 1, is basically you have a layers but you are given the depth at the middle of each layer, at the midpoint of each layer. So it's basically, you need to use trapezoidal rule shifted. So basically, rock bulk layer I, rock bulk layer I minus 1 times G times Z minus ZI minus ZI minus 1. So you took the average of the two layers. Oh, sorry.
Is it like you need to consider the water level, like the water volume as a layer?
The height.
The height as
Yeah.
a layer and calculate it by itself, then add it to the other layer.
Yeah, it's the first layer, basically the water.
It will be water on the
Yeah.
first, okay.
The homework is multiple layers. The water, yeah, it's giving multiple densities because the density of the water changes
Okay.
as you go
I
down.
thought like you have like rock and water, but.
No. Water, rock. Yeah, no. It doesn't go. Yeah, I think this has, you have two layer densities, and then you average them, and then you basically get the average height. And it's another variation. If what I showed on the previous slide is not possible, maybe this equation is possible. There is errors associated, it's approximation. So there is error associated with any of those methods. It's just different way of doing things, you know? It should have a wavy thing here, ideally. But yeah, because it's another way that it is possible. Just remember for the offshore, don't add the weight of the water on every layer, only on the first one of the rock, and then what you have there, you add the second layer, the third layer, etc., etc. And I believe, actually, we might be able to give the first homework after today. Because in the beginning of the class, I was saying, I'm either gonna give it this afternoon for next Monday, or on Monday evening for next Wednesday. So I might be able to give it today, I guess, I'm not sure. Okay, so this is not the only place that you have fluids. You also have fluids inside the rock. So the rocks have pores, and they're basically empty spaces, hollow spaces. These pores are filled with fluid, and the fluid itself is under pressure. And you can see here, you probably know that from your geology classes, but yeah, it's very, very, it's like a sponge, but it's solid, you know, it's rock. It's filled with fluid, and the fluid is under pressure. And now we have some model, we have a model where the whole class is about building a model of how the rock behaves. So we are sort of on the boundary conditions of the model, and the external stresses acting on the model. We talk about S1, S2, S3. We talk about tau shear stresses. We talk about Andersonian stresses. How does pore pressure impact those stresses? That's a good question. And yeah, here it says that the rock is a porous medium, fluid-filled pores. It has fluid-filled pores, and therefore it exhibits what we call pore pressure. Okay, for reference, the hydrostatic pressure, or also known as normal pore pressure, is that of fresh water. So you take fresh water, it has a density of 62.4 pound mass per cubic feet, and it translates to 0.433 psi per foot. Now that's a little bit, it's a smaller number than the overburden, 1 psi per foot. And this is a number that is like an idealistic value in a sense that this is a value for certain set of conditions, like fresh water density all the way down. You don't use this value unless you are told to do that. This is not like the lithostatic gradient that is an approximation. I don't have any indication, so 1 psi per foot makes sense to use. This is like 0.433, you don't use it unless you have, unless you are told to use it. So 10 feet of water, fresh water, 4.3 PSI, right? Non-hydrostatic variations of pore pressure are usually located adjacent to low permeability barriers. So where you have a trap, you can have a fluid accumulation, and the pressure can be, the pressure of the fluids inside the rock can be much higher than the equivalent of 0.433 PSI per foot. This is what we go after as petroleum engineers. We want to see traps with good accumulations, and this is where we're going to drill and try to find oil. Yeah, so we're going to see an example later on. There are several ways you can achieve this, what we call overpressure. Yeah, but generally, you have a trap, which is a low permeability barrier. It doesn't, fluids go in, get there, but they cannot escape. So they accumulate. We talked about some of those in previous lectures, like salt domes, etc., etc. So basically, you lock in there and pressure goes up. Overpressure leads to weak rocks, and we have stability problems, borehole stability problems, or wellbore stability problems. We'll see those in the last module of this class more specifically. And yeah, it acts. We're gonna see mathematically how we model pore pressure later, but generally, pore pressure is a pressure value. It acts in every direction. It's like everywhere. It acts everywhere, so it affects all the stresses, all the normal stresses. Yeah, it provides resistance in all directions, basically. So it affects every normal stress. So you need to, basically, and it acts the other way than the in situ stresses are acting. So if SV is acting that way, pore pressure acts the other way. It makes it, basically, it counters it, it counteracts it. Makes it smaller, so the rock is weaker. This is a pressure traverse diagram, as we call it. It's a depth versus pressure diagram. You have pressure on the horizontal axis, depth given by elevation on the vertical axis. Horizontal axis is pressure. And basically, you have the variation of pressure with depth. And where you see here at the top, you see something that says 10 point, what is it, 1? Okay, and it says there, yeah, this is an important value because it's basically, it says here, quasi-hydrostatic pressure. Why is it quasi? Quasi means little, like almost like less than semi. Like if it was like, we can say semi-hydrostatic. Yeah, but it's like less than that. Yeah. Almost there, basically. Approximately hydrostatic pressure. The reason is that 0.433 PSI per foot value I told you earlier translates to 10 MPa per kilometer. And here we have 10.126. That's almost there, almost fresh water, not exactly fresh water. Same thing as a little bit below, you have 14.7. It gets bigger, but it's not that far. It's not close to 23. That is the 1 PSI per foot. 14 is still quasi hydrostatic. It's like an arbitrary term, like it's bigger than the hydrostatic, but it's not crazy bigger. And then here at the bottom, you have overpressure, you have, okay, you see a value that is less, 9.8, but then you see some values that are like 23.92. This is a very overpressure value. It's extremely high. It's higher than the lithostatic. That tells me that the lithostatic in these areas is actually higher than 1 psi per foot, because there is no chance you can have this pore pressure without lifting the that you are lifting the earth. If SV was 1 psi per foot, which is 23, and pore pressure was more than that, it means that you are lifting the overburden. You are lifting the rock off the ground. So yeah, that's how it looks on a diagram, and you're gonna see in your homework an example of like a log, I think, with different values for SV, etc., etc. Pore pressure can be displayed against depth in a pressure traverse plot. That's what you are seeing on the left. Hydrostatically, pressure regions will follow the line with a slope equal to 0.433 psi per foot or 9.8 MPa per kilometer. That's the exact value of 0.433. It's not 10, it's actually, roughly we say 10, but it's really 9.8. Points on the right is a smaller slope, and points on the left is a bigger slope. Because here, it's a bigger slope, but what is the slope of this plot? The slope of the plot is the units of the y-axis, unit of y-axis, divided by unit of the x-axis. So it's gonna be feet per psi. Okay. So if I see a smaller gradient on the diagram, like I do when I go from here, my slope is bigger than here, right? If I take a point here and 0, and then a point here and 0, my slope goes down, but the slope is meters per MPa. So it's the reciprocal 1 over the gradient of the pressure gradient of the fluid, of the pore pressure. So if I'm hydrostatic, I'm getting 1 divided by 0.433. Or 1 divided by 9.8 MPa per kilometer. That's why a small gradient means overpressure. A high gradient, a very steep line, means under pressure. And that's a mistake I made in the Petroleum final of 2015 in a bonus question. There was a region highlighted, and I said it was like on the right, and I said under pressure because I saw a smaller gradient, but I didn't see it. I didn't think about it well enough. And then John also said, I almost screamed when you said under pressure. Anyway, yeah, that game was close. That game was close.
But you won the next one, right?
Well, the next one was after 4 years. Yeah. But anyway, yeah, that was one of the reasons we lost that game. But anyway, so be careful from this intuitive, it's a little bit counterintuitive. You see a low slope and you think of under pressure, but it's really low slope means over pressure. High slope means under pressure. That's what I wanted to say in this slide. And then a good question is, how do overpressure is created? And there are several mechanisms. We are going to see a very common one. Hydrocarbon accumulations create overpressure due to buoyancy, just like you have in the water Archimedes principle. You get something that has a lower density than the water, you put it down, it goes up, right? Overpressure is proportional to the oil column height, and the density difference between the oil and brine below it. Normally there is brine below oil. So basically, the overpressure is calculated as let's just call it delta PP in this case. How much higher is my pressure from the hydrostatic? Okay, and this translates to the density of the brine below it minus the density of the oil times GH is basically the force. By the way, this is translation from like the theoretical value to the actual field value. That's why I'm using brine. There is brine, not fresh water below oil. So I need to see the force with which the brine is pushing the oil column. And then assume that above the oil column, you have glass, impermeable layer. That's how overburden is created, overpressure is created by buoyancy. Another way is changes in temperature that causes fluids to dilate. If the fluids want to dilate, but you constrain it, you create overpressure, right? Pore pressure increases, exactly. Clay diagenesis expels water molecules. For instance, montmorillonite, which is an inlay, is converted to inlay. Yeah, at high pressure and temperature. Yeah.
Or subsidence sometimes when you have subsidence of the field, so you will see that often.
You will see, yeah.
It's a good indicator of subsidence and diagenesis.
Yeah, they freeze water molecules, and then they are basically they were previously bonded, but now they are added to the pore space. They were part of the rock, and they are no longer part of the rock. They are part of the fluid inside the rock. This addition under constant pore pressure conditions results in pore pressure increases. So you're adding more fluid to the pores of the rock, the pore space inside the rock, so the pressure will go up naturally. Hydrocarbon generation also induces overpressure. The whole generation of hydrocarbons. The original organic compounds transform to another phase, which occupies more volume at the same pressure conditions. So basically, you want to fit more volume in the same space. Hence, overpressure in organic rich shales. That's where the oil is created. It's a good indicator of hydrocarbon pressure. Presence, sorry. So generally, you want to find hydrocarbons at high pressure. Many times where you have high pressure, you have hydrocarbons. So now offshore reservoirs and pressure. The weight of the seawater above formations below seafloor must be subtracted. That's what we were saying earlier. Take the weight of the seawater column and subtract it if you want to make estimation, or add it if you are estimating SV. And then you have this equilibrium compaction from high sedimentation rates in fluvial environments, leading to overpressure, for instance, in Gulf of Mexico. And this is something I want to show you. Let me find my notes. I want to draw it correctly. I don't want to get it wrong. So okay, and then overpressure. I want to draw a diagram. Okay, let's see if we can do it. Last year it took me 2 attempts, but it's I had to erase and try to put everything into one slide today. Okay. You know, a fluvial environment is where the river ends, gets into the sea, into the ocean. Let's find a good environment is where you in Gulf of Mexico. What?
Yeah, I remember this.
What?
No, this is the sediment, like.
Yeah. So it's like this is let's just call it the house. It's yeah, Nola. It's no New Orleans, Louisiana. I'm making it purple and yellow. They are LSU fans because it's North Dakota, because it's Louisiana. And okay, now continuously over the year after year, it's like you get
At that time,
yeah.
that house wasn't existing.
Well, I mean, we're in the it can be the current era. You have the water. This is Gulf of Mexico, right? Okay. Is the delta. And you get continuously, okay, the water flows into Gulf of Mexico, but it's not just water, it's also sediment.
Yeah.
It gets deposited here, 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 right? It gets a lot of seawater. You have the seawater, but you have layers of sediment being deposited continuously.
Basically, you're adding volume to the previous rocks.
Yeah. You're adding stuff on top of it. Yeah, exactly. Now, let's see. The rocks that are being deposited, they are adding up, and you have pore space, and you have fluid in there, etc. And then this fluid, let's make it green, wants to escape. Eventually, it will enter the sea level, the seawater, okay? It will enter the seawater, but it's at a slower rate, okay? We call this with brown, it's the rate of sedimentation, yeah. And with the green is the rate of, well, we're going to call it pore pressure diffusion, which is basically fluid migration upwards. Rate of pore pressure diffusion. Okay. Or fluid migration upwards. Do you want me to write?
No, it's fine.
Rate of pore pressure diffusion, in parentheses, upward migration of fluids.
Yes.
Okay. Now, that's the thing. The brown rate is much higher than the green rate. So the rate at which we deposit sediment is much higher than the rate at which the fluids inside that sediment can escape, or can escape through that sediment. So what happens is that, well, the sediment doesn't have pores when it comes in, but gets deposited eventually. It will make a pore space, and maybe fluid will migrate to it. But imagine, even if the fluid is in the pores of the rock underneath it, you add overburden on top of it, okay? And you add overburden, you compact it faster than what it can be released, because when the fluid enters the seawater, it gets released, right? Pore pressure will go down. but the pore pressure goes up faster than when it goes down. Okay, the brown rate makes pore pressure increase. PP, we are going to abbreviate it with PP. The green makes pore pressure decrease. Sorry. But the decrease is much smaller than the increase. That's what is this equilibrium compaction, and this is what I'm trying to say with this one here. This equilibrium compaction from high sedimentation rates in fluvial environments leads to overpressure. That's what we are trying to say here. Now, I wish I had left space to draw how that will look in a. Yeah, maybe. Let me erase part of it. Okay. And then we have the seawater, and then we have sedimentation coming in continuously. Okay, how does that will look on a pressure traverse plot? That's a good point. So Malek is saying it's going to be a straight line, and he's not wrong. So this is a pressure as before. This is the depth. If you took drilling, we call it true vertical depth, TVD, or just depth, that's fine for this one. Okay. First, you put the density of the seawater, which we said is constant, 0.465. Okay, so for the water, we have this. Oh, sorry. We start from atmospheric, and we go. Yeah, I want to start from 0 PSIG atmospheric, sort of. Something is going on with the pen. Oh, the nose of the pen is off. That explains it. Okay, let me try to get it. Yeah, and then you go down, and then you reach the end, sort of like this, straight line. The reason why it doesn't look straight is the pen. Okay, and then let's just carry it. Oh no, it's not the color. It's where the nose of the pen. Okay, it comes here, and then I'm keeping a straight line. Okay, and then I'm gonna have. We said about overpressure, right? Overpressure is a higher gradient or a smaller gradient?
Smaller.
Yeah. So
the slope is gonna be lower.
Yeah.
So lower gradient.
Like this? Okay. Now, if I'm a good petroleum engineer like Malek, I will come here and say, okay, to my company, Mr. Yeah, no, the people who decide where to drill, yeah. They're gonna come here, you may have oil. Guys, drill some wells there, and let's see. That's an overpressure region.
Yeah.
So you will be, you could be able to have some accumulations there that you can go after. Of course, you are gonna couple it with some other measurements, but yeah. Under pressure now. This is the opposite of overpressure. It's a low pressure, higher gradient on the pressure traverse plot.
It's almost the same as the water, as the hydrostatic.
No, under pressure. This is less than water.
Awesome.
depleted zone.
Depleted, yeah, it
Yeah.
was like,
It's gonna be a higher gradient. Occurs when pore pressure is lower than hydrostatic. The most common reason is that you had a reservoir there and you depleted it.
yeah, the
Or
production, you can see that.
oh yeah, yeah.
Even the porosity and permeability of the reservoir gonna change.
Yeah, if you go to Long Beach in California and you stand by the mountain and you look the city down, you will notice subsidence.
Oh, really?
Yeah. You notice the whole city.
So they had permeability statistics of the,
No, they produced it very fast
oh,
in the 20s. Oh, they were producing, they had wells next to each other. You could jump from one derrick to the next.
really?
It was that bad, yeah.
It was 9-inch maybe.
No, it was
They
like,
were producing from 9-inch.
I don't know what size, but it was like back in the day they were
At that time, they
producing.
were producing with big diameters.
Yeah, it was.
That's why they have chronic water problems.
Yeah, they were producing fast, and it was, depleting the reservoir, you basically lower its pore pressure,
Yeah.
and it's the opposite.
And
Now-
you cannot use it again that way.
No, unless,
You will have complication, injectivity.
well, now they are pumping water from the islands there. They pump the city's water from the Tanzai Islands, which is basically platforms that are
But they cannot
camouflaged.
eliminate anything.
Yeah, it's a very slow process, and they pump like 5% more than what they produce. That's their goal from what the oil wells are producing.
They need to have good pumps though.
Yeah. But every island has 1,000 wells on it, all of them on ESP.
They can have problems in the future of the land instability.
Yeah, but I mean they are rising it, the pressure, but very, very slowly. But the damage is already done. I mean, it's the damage was done when they were like putting wells next to each other and producing them as fast as they could. Because they were also competing with each other. As
Two
well.
companies like those big
A
companies.
lot of companies. It was like a rush. If you see pictures, let's see.
It was easy
Yeah, it was very easy.
because you have conventional, big porosity, big permeability. So just drill and make your completion and that's it.
Okay. But how can I see? So it says, you see how it was before. Oh, you don't see it. It's in the, let me put it here. Can you see it? Like,
All of these are wells.
yeah, next to each other. And then you can see subsidence geologically from,
All of these are wells like that.
yeah, next to each other. They were depleting the same reservoir altogether. And what I was gonna show you this is not an island. It's not like it's a man-made island, but it's basically a rig.
Oh, really?
Yeah, that building that you see here, it's a rig and moves around drilling wells. There is 1,000. I've been to that island, one of them. And there's 4 of them. I have been
So
to.
it's a rig, it's not a building.
Yeah, it's a rig camouflaged, and it's like a rail, and it moves around, and you drill, and then you have. I'll show you pictures in the next class, but also I can show you privately that basically it's a rail and it's like a bunch of wellheads there, and they drill. They don't drill, but they are basically producing or injecting from those wells. In compartmentalized reservoirs, which is basically what we call reservoirs that are divided into different parts. Like the whole reservoir is divided into different portions, and there is a limited connection between those portions. So it's like, it can be fold, it can be any way that the reservoir is basically compartmentalized. It's like divided into portions. It can lead to areas where it's more pressure than others.
No, yeah.
Either higher or lower. So degree of compartmentalization Actually, since we are talking about the back in the excellent 1920s in LA, you can also talk about a lot of water flooding problems in compartmentalized reservoirs. A lot of problems in reservoirs that were trying to water flood back then, not just in California, many places, where they were, it's because of the compartmentalization of the reservoir, it makes the water go one way, where you try to make it go another way. It's sort of like heterogeneity, but a different kind of heterogeneity. Well, I don't want to call that heterogeneity because heterogeneity is something different, but basically it's like I have a reservoir and it's divided into parts.
Different blocks.
Yeah. Imagine different blocks. Yeah, that's a good analogy. Reservoir depletion also alters the in situ stresses, so it impacts that SV, SH max, SH min we were talking about, just like overpressure does. And there are implications in that. Okay, so we talked about the in situ stresses being affected by the overpressure and the underpressure, right? Mm-hmm. And now a question is how, mathematically how, to what extent are they affected? Are they affected the same way? Are they becoming bigger? Are they becoming smaller? How? And we talked a little bit, but we didn't mathematically say how, explain how. So the in situ stress states S1, S2, S3. When you hear stress state, think about it, you want at least 3 numbers to hear. You want 3 stresses, 3 stress values to hear. So let's modify those S1, S2, S3 that we mentioned in the 3rd lecture, I believe, to incorporate pore pressure. We're going to have 3 new stresses, versions of those, and they are going to incorporate pore pressure PP. So now we are going to have the greatest stress, it's going to become sigma 1, the Greek letter sigma. You know, the Greeks have 3 sigmas. They have, they have the capital, the uppercase sigma, they have the sigma that is in the middle of the sentence, and they have the final sigma, which is S, which is at the end of the, not the sentence, of a word. So my name ends with S, it has this S, right? But if I had sigma in the middle of my name, it would be the middle sigma. Yeah. Here we use this sigma for what we call the effective stresses. So we have S1, we subtract PP from it, and it becomes sigma 1. Same thing for the intermediate stress and the least compressive stress. Okay, so now I had S1, S2, S3, and I got sigma 1, sigma 2, sigma 3. Okay, now which one of the sigmas is the most compressive? Yeah, which one is the intermediate? 2. And the least is 3. So the ranking remains the same. Just like you had S1, S2, S3, now you have sigma 1, sigma 2, sigma 3. It's the same stresses. You know why? Because pore pressure acts equally in all directions. So I'm subtracting the same number from all. If I subtract 3 from 8, 7, and 6, it becomes 5, 3, and 2. So 5, what was it, 6? 3 and 2 or something, or 6 and 5. I'm subtracting a constant value from, so the ranking remains the same. So if I had normal faulting stress state, if I had strike slip, if I had reverse, it remains the same if I change the pore pressure, at least at that level. There are some times that you can get different stuff, but the pore pressure affects everything the same way. because it acts the same in all directions. So yeah, the ranking remains the same, the sequence remains the same, and the same Andersonian stress regime. Oh yeah, same thing about the Andersonian stress regime. SV becomes sigma V. SH max becomes sigma H max, sigma H mean, etc., etc. You know, as petroleum engineers, pore pressure is very important to us. So many times when you work on a project, people are giving you the effective values. So be careful when you are dealing with effective or with absolute values.
Like with or without pore pressure.
Yeah, is it S1 or sigma 1? And does the other person you are talking to, when you tell him sigma, does he understand it the same way as you understand sigma? Because they may not be using the same nomenclature. I'm telling you the nomenclature that most of the people are using in geomechanics, but it doesn't mean that it's always like that. Same thing in Cartesian coordinates. What if I have, okay, SXX, SYY, SZZ.
Equal to sigma H.
Yeah, I subtract pore pressure from all of them, and they become, the S's become sigmas. Yeah, same thing, same idea. Pore pressure acts the same in all directions. And I think that's a good point to stop. When shall I give the homework? Today or Monday? Shall I give it today? I can give it this afternoon and make it. Well, if I give it on Monday, it's gonna be due next Wednesday. Next Wednesday.
Okay.
I want to give it tonight, so it's gonna be due the Monday, the 23rd. That gives you 1 office hours session to ask me any questions that you have. So if I give it today is the 13th, and I'm gonna have it on the 23rd due. And yeah. Thank you, everyone. I will see you on Monday. Have a nice weekend. Well, you have 2 weekends to work on the homework, which is, yeah, it's gonna be fairly, it's not that tough. It's not that tough. It's fairly easy. And next class, I will go over it very quickly. Yeah. Anyway, thank you very much. Have a nice weekend, and I will see you on Monday. Stop record.